All right, so the homework, right? It was pretty good. Like everyone did well on it. Let me just go over a couple things. So let's see. So let's see. This one was okay. So like anyway, I said like anyway, some people like a lot of the questions were like draw a cartoon, and some people just didn't do that. So that was anyway, but mostly everyone did. So it was good. Then this thing from slide 73. So people successfully kind of copied what's there, but it let's see. I already did that. Let's see. It should be open already. Slide 73. So that was good. So they got like basically, so you get to this point, you have to take an integral of this thing. Like you have to take the same thing that you do with this, like you have di over I equals dx, delta dx, and then here you have whatever that is, you have d, that correlation is whatever cs that he has in the paper, right? This would be like cs, and then this is equals minus cs. That's why it's a linear relationship. Then you do an integral of that. So you have dx over x, the integral that's ln of x, then integral of ds is s with the limits, and then you end up with if you take an exponential both sides, you get the cs thing equals exponential whatever the answers is this thing. So anyway, one group successfully did that, so I give them 5 extra points. It's like if you anyway, no one else, everyone else kind of got to this point and did. So the point of that is like what is like they always say linear absorption, and it doesn't look linear, but decay function, right? This is just an exponential decay. Like you start at the I0 and then it decays down. So anyway, how do you get exponential decay and call it linear absorption? That's the issue. And the reason is the change is proportional to the thing. Like the intensity drop is proportional to the intensity, right? And the same here. So the stronger correlation you have, the bigger the change in correlation. That's what's linear. The change is proportional to the thing, so it's linear. So it's equation of a line, right? So and then when you integrate it, you get the exponential. Is that okay? Or I hate to beat a dead horse, but it seems to be like, to me, like when I saw like linear absorption, Beer's law, and it didn't make any sense. It's an exponential function. So that's all. It's kind of a nuance, I guess. All right, and that, what else? There might be one other thing here. Comment on Chen. Yeah, this was all just whatever he said was okay. I mean, it's just like your opinion on it, basically. I think this is, we already talked about that other parts, and everyone did okay on that anyway. So the rest of it doesn't matter. I think but one person did find so the 2L thing that where he swaps out the whatever I just had. Swaps out this function for S over 2L. So one person found a paper that talks about that, but also doesn't really drive it. And it's like a lot of math. And then inside that paper, there's a reference. I looked that up. And that's like even more math, you know, none of it even makes any sense really. I mean, even once you read it, it doesn't, not this, there are 3 references to that over 2LP, but none of them really make sense. The other thing is they talk about LP equals like a spring constant. So let's see. They talk about this thing. So hate to go to .cam because I've had complaints about my writing. There it is. So there's equations that go like,
Oh, you're blurry.
might be better blurry. That's an improvement. So, anyway. Yeah, the writing actually comes in focus when it's blurred. It's like code here. So anyway, this thing like you can have this thing and you say like there's a torsional spring constant. So you say like the force goes to the spring constant by the change in the angle, something like that. So you know for the spring constant, it's hard to bend. So the amount of hardness to bend is this kappa, or they call it beta for bending, I guess. They say that persistence length goes with beta, and then they come up with this thing like by KT. It's like, in other words, I guess the modulus is force per area, and then but this modulus is force per angle. Anyway, somehow it ends up that you get units of length from that. This is force times distance energy, and this is usually force per area. So somehow you get length out of that, but that doesn't really work. So anyway, the units don't seem to work out for that too good. But anyway, this is the equation we'll see. The problem is, and it's kind of like a balance between us, like this, thinking like the thermal makes it want to flop around, and then this springiness wants to make it straighten out. So there's an opposition between a ratio between the two. The problem is like there's almost no like temperature dependence. This would be like a really strong temperature dependence to the persistence length. Like the higher temperature, the persistence length would just like take a dive with that equation, maybe like LP or something like that. Right. So, but in fact, LP is just constant in temperature. So there is no. So this is a theoretical function that kind of makes sense to look at it. But in fact, this thing doesn't change with anything. Like you can take the polymer, put it into dilute solution, put it into a melt, mix it with other things, good and bad things. This thing never changes. You change the temperature, it doesn't change. So basically, this doesn't seem to be true experimentally, that there's any dependence. So LP is like a fixed number, basically. So for whatever reason, that's kind of just an observation. Anyway, so that's that. Those are the things I got out of that. But just because the guy who found, or woman, because I can't tell unless you put the names on the top, because it just goes by group 1, 2, 3, 4. So I never can really figure out who it is. But I have a hunch who it is. We did that one, but basically they went and found a paper and talked about it and stuff. So I gave them 5 points for that too, like extra. So you can get extra points. You can actually get maximum probably 120 on one of these if you want, like if you do a lot kind of things like that. But I mean, the undergrads, you don't need it. Basically, if you want to, for bragging rights, whatever. But anyway, so I lost track of whatever I was going to say. Oh, let's see. Oh, because he was the one that went into those other papers and mentioned this temperature dependence thing. So anyway, temperature dependence isn't really part of the picture for persistence for whatever reason. The coil, like the chain changes size with temperature. Persistence is kind of a fixed, pretty much a fixed number. Anyway, so yeah, all right. I also figure out what I'm doing. So that is 44. I'm gonna go there in a second. So I went to we went through this stuff, right? 2 times, once speedily, once slower. Wait. So the idea here is you have in terms of time, so you have just a progression from now to the future. So it only goes in one direction, right? And then on this side, you have position in space, which can go any which way, like left or right. So you have plus and minus. So the linear term, first derivative drops out of the Taylor series. You just have the second order, which makes, in the first lead term, because this is a normalized function, the integral of it is 1. So those 2 terms cancel. So you just have the second derivative as the first derivative, time versus space. So time is linear, time is progressing in one direction, space is in both directions, if it's 1D, right? And that equation, the solution to that equation is the Gaussian, right? So that's kind of the key point of that business, is this Gaussian, not that Gaussian, this Gaussian, right? So it's an exponential minus something squared, and the thing below would be 2 sigma. So 2 sigma squared. So sigma squared would be 2dt here. Sigma squared is 2dt, which is also the second moment. So I'll show that later. Anyway, so the question is like, how does that relate back to the polymer, right? So you have, so the polymer, let me go back here. So just a little bit of a jump to say that's a polymer. So you have, in one case, you have a diffusing particle, and then it's going in one direction, kind of, and then it's got time. Time is 1d, or one direction, and position is two directions, and that's how you end up with the square thing. D whatever, s dx, and then this one you end up with the first derivative. So then setting those equal, you get the Gaussian from that. But when we do the walk, like, so we're doing a walk to make a chain. So we have a chemical bond. So if we say it's a random walk, right? So yeah, it's kind of like the path of diffusion, but if it's really random, then it can go back. And this thing can't go back, right? I mean, it's basically time doesn't go back, but n. So we're saying that we have nl squared, and we have t 2dt is x squared. So r squared is nl squared. So time and n are partners here, but they're kind of different. Right? In other words, I mean, you can polymerize in either direction, for instance. Right? So anyway, so one way. So if you want to look at that, then you need to worry about refusing to go backwards. Right? Say, so that's not a random walk anymore. In other words, it's not necessarily a random walk anymore. Because if you say random walk means I can choose any direction I want here. And if I say I can't go backwards, I'm only going to progress forwards, which is what gives rise to the end of the one here, like t to the one. Because time can only go forwards, the n can only go forwards. Then that's kind of a problem, right? So that's the problem of the short range interaction. If that doesn't affect, so you have to consider. So we did this like sum of r dot r ij to n. So that's j r squared equals that thing, right? And then we said if I doesn't equal j, then that's 0. And then if I equals I, there's n of those, and then this thing is r squared. So that's where we get the nl squared number, right? So the cross terms disappear. But if you don't have that back term, this isn't true anymore. Then you have to kind of consider what's going on there, or with the other one. So it turns out the answer is it does have an effect, but it affects L. It doesn't affect the scaling of N. So you end up with NL like a new L squared is larger. So new L is bigger than the old L. Right, so that's kind of the idea. So you can. So this is from this book by Doi, which is it turns out like it's a pretty good book. Like it's pretty simple. So Edwards was a guy that should have won the Nobel Prize, and de Gennes won it in France because they didn't want to give it to England again. And then he became knighted instead. So it's like Sir Edwards. And Doi and Edwards wrote a book that's unreadable, like a polymer physics book that's unreadable, but it supposedly comes out with the idea of reptation in it. You can dig out somewhere, but it's a mess. And then de Gennes, the guy that did win the Nobel Prize in that year, or whenever that time period, wrote another book that's equally kind of unreadable, a little bit better, but almost unreadable, on this kind of the same subject. And he took Edwards' stuff and kind of put it in his book, right? So it's kind of like there was a lot of argument between the British and the French over who deserved it type thing. And Doi, the book is Doi and Edwards, and Doi is the guy that wrote this other book. So, which I'm going to show here if I can get into this thing. But Doi is down at the bottom. It's like one of the first things here. It's like this book, right? So this it turns out is like, so almost like in penance for writing a book that nobody could read, he decided he'd write like an idiot's guide to whatever, polymer physics. And this is it, right? So it's kind of like absolutely the simplest thing. Like supposedly monkeys can read this, it's the kind of thing. So, sorry, 95, so it's old, but, oh, sorry. Yeah, so it's on the web page, you can get it. Anyway, it's like in 95, it's called like Doi, whatever. Joy, Intro to Physics, whatever. And then, so the first part, he goes through this problem, so in fact, it's like this, so what we've been doing, you could just read this and it's like right along the same thing, pretty much from 95, so nothing's changed too much. That's a Gaussian thing. Then he gets to this point, so this thing right here, this section is kind of what I'm going to, 1.12 is what I'm going to go through. So basically it's the same as what he has there. So, and it's on slide 44 here. To deal with this issue of it isn't a straight line, right? So you say, like, we know that this thing's, so if you take the first, like if you're going to take a random walk and it can go in any direction, the average of that on average is going to go to the starting point. It's never going to go anywhere because it's like can go left, right, top, up, down, in, out. And it's always the same probability of each direction. It will end up 0, right, for that. But when you don't select the back step, it's not 0 anymore, right? So anyway, that's what this DOI thing is. So basically, so if you don't, so if you take the random one, it's got to equal to 0. The non-random one is like this. If Z is how many, it's a coordination number. It's like 6 in a Cartesian. So you go like X, Y, and out, up, down, whatever. So plus minus for X and Y and up and down. Right, so that's 6. So, and in reality, Z could be a big number. It could be like huge. Like you aren't really confined to Cartesian coordinates. Anyway, so, but nonetheless, one of them you can't do. So it's going to be Z, whatever that number is. So 6 is a convenient number. Minus 1 times what this, the average. So the average of all those 5 other directions over all the possible choices. So it's going to be a direction away from the original one because you're not going backwards, but it's going to be, so it'll be 6 of those, and then it's going to be like minus the one that you didn't take. Right. So if you say that, and this thing equals 0, that means you can kind of pull this guy over, divide by the Z minus 1, and you can say what that average step is going to be. You can define it in terms of the step. And it's just modified by a prefactor. Right. And then instead of saying this thing about separating these two into 2 different things, you just say, well, I have this function for what it's going to be, like the distance. So the probability of, say it's like a probabilities multiply. So if you're 1 step away, it's Z minus 1. If you're 2 steps away, it's Z minus 1 squared. If you're 3 steps away, it's Z minus 1 to the cube. So these probabilities just multiply. So basically, you can go through your sum. Instead of breaking into 2 parts, just have 1 part. And it's the same anyway, because the I and J difference will be 0. So this will be 1 anyway, if it's the original one. So you have NL squared as part of this argument anyway. But you have this modifier to the thing, which is 1 over power. So the 1 over power, or the sum of a power. So the sum of a power is this geometric progression thing, and it's just got an answer. Like if this goes to infinity, so instead of n, so you say you have a really high molecular weight, you just say infinity. Then you can say you have a geometric progression. Then that thing has a solution, the prefactor divided by the 1 minus the thing. And the thing here is 1 over Z minus 1. And if you plug that in, you get Z over Z minus 2, and then NB squared. So the original thing we had, NB would be the step length, a different name for it. So NL squared we had before, and it's modified by this number, which is going to be bigger than 1. So it's like, depending on what Z is, right? So if Z is 6, this is like 6 by 4, so it ends up 1.22. Right, so you've taken, or 1.22 squared, so take the square root of that, you get how B is affected. So it's 1.22. You've increased the step length, but it's still linear in n. Like it still follows that Einstein function, because it still has time to the power 1 equals size squared, or distance squared. Right. So and this is true of, so this is absolutely the simplest possible short range interaction, and you just analytically get an answer. Right. If you want, you can do more complicated things like include the bond rotation. They're going to follow exactly the same thing. You're going to end up using this same power series geometric progression rule and end up with an expression where you still have a step length. It's just a bigger step length. The more constraints you put on it, the bigger the step length gets. but it's still dependent on n. You still get an n dependence. And it still obeys the Gaussian thing from the Debye, from the Einstein, right? From the Brownian motion Einstein. So you still have a Gaussian function to describe the chain. So this doesn't affect the chain scaling, the Gaussian behavior at all. It just changes the step length. In other words, it's just like magnifying the chain out further, right? I mean, so basically, so that's kind of neat. Like, it's nice. The way he did it's pretty nice, you know.
Is I just want to make sure I'm reading it right. Is B the Kuhn line?
B's the whatever NL squared is, so L, it's a step length. So it's kind of, you're doing kind of a walk, so it's not a real chain exactly. Yeah, it's a Kuhn length. It's exactly the Kuhn length. Yeah, that's right. That's the Kuhn model. So the thing about doing a step walk is a Kuhn model. Right. So basically, yeah, it's the Kuhn length. B is the Kuhn length. Those are the only two things that, like in that paper, in the paper that the guy brought up, he calls it P, like persistence length. So there are like different symbols people use. L is like an easy one, small L, big L is the contour length, the stretched out length. And B's all in kind of in a physics end of things, like the Jens, Edwards, and Doi, B for that. Like by convention, they just, that group of people and everyone that kind of read their stuff uses B. Then kind of the chemists, I think, use L. So, and then the P, I don't know who uses that, but this paper uses P. So you can use whatever number you want. You just have to look for, what you're looking for is this dependence, like the number to the power 1. Then the thing squared is the thing squared. The units have to match anyway, so it has to be length squared. Right, so, right, so and if you want, like, maybe if you took with Eero's class, like they went through the thing with Florey's stuff and the rhythm theory, and like, so you just plug in, like, instead of saying that one minus z function, you end up with cosine of the angle, then you end up with a matrix, do the double sum, and you have that's the probability, this angle, the 109-degree angle for the carbon-carbon, and then you go through the same routine, and you kind of end up with the same thing. You end up with NL squared as the lead term. This is kind of the same function that we have, this 2 alpha, 1 minus alpha, right? So it's like the simple Doi thing is much easier to understand than trying to plow through all this stuff, which you will never use. Like this is stuff from the 1960s, and it's, you know, this kind of, like, you won't find a paper where they're talking about this stuff. So basically it's gone. It's like historic. The Doi thing is so easy to do. It's like much easier, much kind of better, unless you know, so anyways, kind of ignore that stuff. All right, so that said, I want to go back to this Gaussian function, whatever that is, this thing. So last time, so anyway, so this function's based on the idea that we have this, that we can say Brownian motion is the same thing as our, let me hide this, as our chain, right? Chain doing these steps. So basically it's important to kind of say that's true. And I think you say that's true by going to look at that Doi books, that chap 1.2 or whatever it is. It kind of does that. But wait, so assuming we can use the Gaussian function to talk about the chain, we haven't figured out where this term comes from yet, the prefactor, but this normalizes it. So the integral of this function is 1. Right, so that's a normalization factor. This doesn't depend on R, it's just a number. All right, so it's just a prefactor. So anyway, and then you can say that the chain, the way that the chain gets there is by kind of thermally moving around. Like each of the Kuhn, so the Kuhn unit itself has one conformational state. So it's got 0 and then all the entropy of this chain is going to come from this conformation of the thing, like how it's wiggling around like a worm kind of in space as it's writhing through space, right? And it's sometimes collapsed down, sometimes stretched out. It's going through all these motions, and temperature is kind of what's deciding that. And there's an energy associated with this kind of writhing around of the chain, right? So Boltzmann's law will describe that. So this is an entropic description of something, right? So this is an entropy equation. So you have, so let's see, I've got to go over here. So there's no, so we have like, the ln of the, so you say a probability you have of something happening. And then KT, that's like, or K, that's S. And the energy is minus ST. So that means it's KT ln of some probability of something happening. That's like the thermal, the first part. There's different ways to look at thermal. One is like flipping coins and calculating the entropy. Like when they get to the entropy part, there's a flip coin part of thermal. I think every class does that. Anyway, this is the probability would be like a bunch of factorials. And then ratios of factorials, and you get the entropy from that. Right. So this is just, so basically that Boltzmann equation for energy is the same as that first, like thermal class when you first introduce entropy. You say it's like a probability thing. So you say, so if you take exponential of E over KT, let's see, this should be minus here somehow. Anyway, P is E to the minus energy over KT, and the energy in this case is like entropy. Entropy times temperature, kind of, right? So it's an entropic equation. There's no enthalpy in this. If there was enthalpy in it, it would be non-temperature dependent term. So kind of have a different form for the argument. Right. So the Polymer chain is an entropic chain. That's another way to talk about it. Entropic chain. Right. So it doesn't have any, there's no interactions except for the local ones that make the things have longer steps. There's no, the chain units can pass through each other. There's no energy of interaction, there's not even a hardcore excluded volume. So the chain, theoretically, it can just pass right through itself. Right. On a local scale, it doesn't matter. On a global scale, that matters. Right. So basically this equation is describing an entropically driven system. There's no enthalpy of interaction between the units. And then we can put in our 3D Gaussian, where NL squared is sigma squared times the chain length squared. Right, that's another probability. So they're both exponential minus. So this argument, and that argument have to be equal to each other, which allows you to say what's the energy of a chain as a function of its size, end-to-end distance. Like the distance from one end to the other. That distance, right? So that function is going to be that the energy is just going to be KT, so Boltzmann constant, and then 3/2. So this one's 3D. That's just from the Gaussian thing. NL squared and then R squared. Right. So that's a nuanced thing at first, but then if you realize, so if you take the chain, you want to stretch it. Okay, when does that happen? Well, it can happen if you stick a chain, tether it to a surface, and then use an AFM tip and pull it out. Like that's one way to do it. That's a hard way to do it. Right. Another way is you take polymers and end link them. Right. Like you could put hydroxyl groups on the end, and then put in silanol functional group, like a tetrafunctional silanol, and it would bond and give off water here. And then you can just make a network of these things. So you make a rubber like siloxane rubber. It's going to have these chains like all linked together. And then after a lot of geometry to figure out how that translates if you pull on this thing. And how is it that a single chain unit's going to stretch in it, right? So, but anyway, you can do that. That's done in this book. I think the book is in here. Let's see. Yeah, let me see if I can find the book though. I think it's in here. Whoops. Let's see. What's the name of the book? Just rubber. No, it's not it. That's a tree lore. So that's the original book on rubber elasticity. All the math about calculating from the chain to the actual piece of rubber is in there. That's a good, it's kind of a seminal book, I guess, a British author from, I think, the 1950s or something. But anyway, you can. This is like the book on rubbers. I'm not sure when it was published. Oh, that's pretty small print. Huh? 75. First published 75. There goes the 50s. Anyway, so this is a pretty good book on if you want to know about how rubber kind of how you get from this equation to that. But if you want to get the force, it's the change in energy with distance, because force times distance is the oops. Yeah. So force times distance is energy. So change in energy with distance is force. Right? So the force on the chain is going to be the derivative of that, and you end up with 2. So derivative of r squared is 2r. So you have r and the 2 cancels. You have 3 kt over squared. That's like a spring modulus, spring constant. In other words, if you the force and distance and the spring constant. If you divide force by area, then you can somehow get this to be stress and strain. And then this becomes kind of the modulus, the tensile modulus for the thing. And so you can say that E is going to be proportional to 3 kt, or here RT, because it's moles, and then the molecular weight between cross links and C, and then whatever step length there is. Right, so you just take a rubber and stretch it, get the modulus. You can calculate the molecular weight between cross links, like what molecule size is in it. Right. And then if you change the temperature, the modulus increases, or there's a tensile force increases. The tensile force pulls back, so you can make a wheel with rubber bands on it, and then put a hot air gun, blow it on it, and at this end of the wheel, the things contract, because when they're hotter, they contract. And at this end of the wheel, because they're colder, they expand, and you can make the wheel turn like an engine. So you make a rubber band engine if you want. I mean, I think you can find a Google. I think there's probably a video. It's like that. See there is. Someone probably is doing it.
This is a demonstration called the rubber band.
Yeah, we know about that.
This one as balanced as we possibly can.
Just turn the wheel on it. Oh, it doesn't work. This I seen. I first saw this in a guy when I was in grad school. The guy had this set up in his lab in a corner. I was like, "What is that?" That's a rubber band engine. Anyway, he got his to spin pretty heftily. This one doesn't seem to be doing much. I think you can find another video where they do it better. Anyway, the idea is like the heat makes it contract. So it's the opposite of a piece of metal when you heat it. Oh shoot, sorry about that. Well, you didn't miss anything. Sorry about that. All right, so anyway, yeah, he just shows it kind of turns. There's better ones, right? There's got to be one that's really going here. This guy looks like he's doing it better. This is more like all right, so the guy's name was Ferris. He's dead now. But so they called this the Ferris wheel. I mean, because the guy's name was Ferris, it's like, it's kind of a joke, but anyway, his would like go crazy. This is ridiculously slow, but his would actually go like spin,
It's using the heat to.
When you heat the rubber band, it contracts, and when it gets cold, it expands. That action somehow makes it. You can do it yourself, probably. Hopefully better than these guys. Yeah, it's so much fun, It's like, this is like a nerd project. So, what did you do this weekend? I made a rubber band engine. How to impress girls, It's like, so. All right, so let's see. Anyway, so what we got here? So that's something completed today. This thing. All right, so that's just this thing, right? So it's just you can get this equation. This becomes like a fundamental equation to predict behavior of plastics, basically rubber, plastics, single polymer chains, basically anything that's like a go-to equation. It's like the rubber elasticity equation. And that's in Florey's first book, like there's a chapter on rubber elasticity, and that's how it begins. So Doi copied someone, and Florey's kind of like the original rubber elasticity guy. Even Preller copies Florey kind of in his book. So everyone's copying everyone else. All right, so this Gaussian function becomes like important to this whole operation. So for instance, how do you get, so we know, so we know Gaussian means that it's like 2r squared, 3d would be 3. If it's 1d, it's just 1 over 2, and then sigma squared. But how do you know sigma squared is NL squared? Like that's a question, right? And then how do you get this prefactor for this thing? How do you normalize the Gaussian? That's another question. And then what else? Then basically how do you get, basically how do you know sigma squared is NL squared? And then what is this prefactor, right? So I think those are the two main issues here. So we have, anyways, let me go back here for a second. So we have the Gaussian, 3 r squared over NL squared 2, right? Then we have, if we multiply that by r and integrate it, we know that goes to 0, right? So we can plot these out to show, like this is something that's in some books, right? So that's the Gaussian function. If you do just r times e minus 3 halves r squared and L squared, then you get, well, r is positive over here, right? So it's r times this function. So it's going to be kind of like that function, but like that. And then all of a sudden, r is negative on this side. So it goes like symmetric, but over here. Like that area and that area are equal to each other. So they cancel. So that equals 0. Right? And then if you're going to find like what's r squared, then you're going to do integral e to the minus 3 halves r squared and L squared. And then that function looks like this. So when r is 0, that function is 0. Let's see, this function should have gone to 0 too. I guess I didn't do that right. It should go to 0 here. Because when r is 0, it's 0. When r is 0, it's 0. And then this thing is trying to look like that, and r squared is trying to look like that, right? But this thing is a steeper decline, and r squared increases. When you multiply them, you get like this. Okay, and it's symmetric because r squared symmetric. So you get an actual value. And this r squared value of it is somewhere out here. It's not at the peak. So the peak is the median of this. The peak is the median value. Also, it depends on L squared, but it's got a different prefactor in front of it. Right. So there's two ways to get the coil size. You can get the median, or you can get this root mean squared. Right. This is the RNS value, like r squared to the 1/2. Okay, so this is the thing that people kind of gravitated to until they realized that when you look at a coil that has interactions, you can't get that value. You can't calculate it because the math doesn't work out. You can't do an integral of that exponential. So you have to use the first derivative, find it where it's 0, and get this median value, which also has the same n scaling. So the two features of that curve both scale with n to the power 1, meaning that it's like it's the Gaussian thing. It's a Brownian-Watt thing. So anyway, those three plots are kind of, so this is probability, and this is r. This is probability times r versus r, and this is r squared probability versus r for x and y. And so it's kind of like that picture. You'll see that, especially you'll see this one in books, and you'll wonder like what he's talking about. For instance, like when you wait, let's see, when you go back to oh, sorry, yeah. When you go back to this guy, wherever that was, this thing, I think this is the thing. Oops, object. We'll do it now. Yeah, this thing. So if you do multiple chains, whatever, random walks performed. So do like 100 something. And segments per interlock, that's all okay. Go. So then he plots, what does he plot at a peak? That's R squared, probability of R, that's R squared he's plotting, frequency of R squared. That's why it has a peak in it. And he says, see, he says RMS is out here. The peak would be like the median. If I did more chains, it'll get to be a smoother, like a hump. And then it's got the RMS is over here and the peak's gonna be over here. So they're in like, so, and later on we'll get the derivative of this to get the peak, to get the scaling for the self-avoiding walk. And then this is RMS you can't get for that one. So right, that's kind of that part of that stuff. That's why he's showing this plot. It doesn't look like, I mean, it doesn't look like a Gaussian or anything. Right? So 0 is over here. That's the R squared number he's getting. Anyway, so that said, all right, so then you want to get like moments out of this thing. I actually had some stuff I wrote down about this stuff. I don't know what I did with it. It's on my desk. Anyway, so we want to get the moments using this Gaussian, and you immediately run into a problem. So that this exponential, so let me just go back over here. All right, so if you have integral of exponential of like kx squared dx, this has to be like 2x here, right? In other words, the derivative of x squared is 2x dx, right? So that would become the same thing as the integral of exponential of x dx. Just saying x is this 2x. X is x squared, then that would work. So you can solve that one. And the integral of that's exponential of x. It's like it's exponential plus a constant. But basically exponential has it's the same, it's an integral. In other words, you take a derivative of exponential, integral exponential. Right, so it's got that feature. All right, so you need to have this right argument, which means the only one that you can solve is if this is x here. Right, but we want to solve, first we want to solve to normalize the function, we want to solve like that one. That's how you normalize. You say that should equal by definition 1. You put a k here, solve for the k, and you can normalize the function. But we can't do that. Then the next thing we want to get is like r squared, which is integral r squared exponential k x squared dx, which this isn't the one we can get. It's not that one. It doesn't have r in front. We can get average r, that comes out to 0. That one we can solve, but we can't get the r squared one, not with normal math techniques, right? Because you only have that exponential. So you have to somehow like work around that. So and this is from a guy called Ed DiMarzio at NIST, who's kind of retired now, but I took a course with him a long time ago and he went through this. Let's see, the mouse disappeared. I can see its actions, but I can't see the mouse. It's there. No. Let me just do something like go somewhere else and see if it works. Yes, that worked. Okay, so this is directly stealing from this stuff. He was much better at math than me. In fact, he just did math. Like he's like a kind of a genius. He was a lab technician at the National Institute of Standards, and then he got his PhD at night at Catholic University. And then he became a staff member, and then he eventually became like the smartest guy in the place. So it's kind of like worked his way up from kind of total grunt to like whatever, right? So he's an impressive guy, really easy to get along with, you know. Anyway, so he had this math thing. So basically, and no one, any book you pick up on Palmer's just skims over this and doesn't tell you that you can't do any of these integrals. So that's kind of a problem because it's the main thing about Palmer science is this Gaussian thing. Right? So anyway, so we want to get this normalization factor, that integral. So you say, well, you can't get that. So this is how Ed DiMarzio did it. He says like you square the function. So and then because you're squaring it, you can square it with anything you want. So you say the two things are like x and y. So you have the function and then the function with y. Then you rearrange the integrals and you get multiplies like 10 to the 2 times 10 to the 2 is 10 to the 4. So you add the arguments to a power. So you add those here, you have y squared x squared, which is the same thing as r squared. So that's the trick he does. He does that, squares it, y squared x squared, that becomes r squared. And then instead of integral, when you change to cylindrical coordinates, then you have like r dr as the argument of it, right? And then d theta. So the integral of d theta is no theta in the exponential, so that just is 2 pi. Then you have integral of r dr exponential ar squared, which is the thing you can solve. So you solve it and you find out that you have, so the pi carries through, you end up with pi by whatever the argument was, alpha here. It just comes out as a number. So your answer to this integral is the square root of that. Square root of pi by the whatever the prefactor is. Right, and we have like this whatever prefactor we have. Right, so that solves that integral. And then the other trick he had, which is, so I think this is like, I would never think of this. So basically, this is what I call like really math whiz type thing. The other math whiz thing is so you need to solve this squared integral. Well, you can't do it that way. But you can, what he did was he figures out that this integral is the derivative in terms of not x, but in terms of the prefactor alpha. So if you take that prefactor alpha, so you take the derivative of this function in terms with alpha, then the x squared comes out front. It's sweet. Like it's really sweet. If you like math, this is like a sweet thing, It's just like you can solve it just by take the derivative with the other thing. You would never think of doing that, right? So just do that. You get like, boom, you get the expression you want. You find out that this equation is just the derivative of g with alpha. And you already know that g with alpha is a square root of pi over alpha. So just take the derivative of that with alpha and you get that that integral is this pi to the 1/2 to alpha to the 3/2. Bingo, And then you just plug in those two things, you can get r squared. You plug it into the first term, you can get the prefactor. So all the problems you have are solved by these two little tricks. Right? So I mean, I don't know, I was pretty impressed when I saw that actually. And then in retrospect, I was even more impressed by it, because it's like, no one would think to do that, Anyway, at some point, somebody did think to do that. So, I mean, it's good. Then we have an answer, like we know what this prefactor is because you can solve that integral. And we also know that r squared ends up being sigma squared. And because we know the answer to r squared as NL squared from that summation we did, you can say that this function, that sigma squared here is NL squared. Right, so that gives you this kind of the governing equation for Polymer chains. Right, so anyway, I think it's interesting, but right, that's kind of how you do that. So it is possible to derive this whole function. Like first you need Einstein to say like this applies to a chain, then you need those two math tricks to figure out what the prefactor is and kind of how this fits together, like why it's NL squared here. And then once you got that, you have this equation. But without that, so in books you just see that equation given. They won't even say the 3 is for 3D, things like that. But anyway, so, and that's also why it's not 1/2 here, it's 3/2, because it's 3 of these multiplied, the probabilities multiply, so you get 3/2. Right, so anyway, so that's that. That's that business. So anyway, so that's good. So you have this issue that and there's 5 minutes I can go through this. So this means that this is a 2D object because the mass goes to the size square. So if you have like a disk, which is a 2D object you're familiar with, you have like the mass of the disk goes to the size square. If you double the size, it's 4 times the mass for a disk, right? With a rod, the length of the rod goes with the mass. With the disk, squared goes with the mass. With the sphere, cube goes with the mass. So this thing's like the dimension of it, right? So, but this thing isn't a disk. This is like spaghetti, and the disk is like a plate. So you have the difference between a plate and spaghetti that this equation doesn't give you information about, right? So the question is, so this is called a mass fractal dimension 2. It's a 2-dimensional object, the Polymer chain. So the question is like, how do you distinguish between the spaghetti and the plate, right? So in order to do that, you need to know like something else about it, and the something else can be another dimension. So if you take an object like this thing, and you say, say I put electric current through it, and I'm gonna have this path through it, where the charge would pass through. So that's the conductive path through it. Right, and I can take that out of the object, and that's also some dimensional object that its mass goes with the size to some dimension. Right, if it's a stick object, then that dimension is 1. It'll just be a straight line. Right, so, and then the other thing you can do is you can say, forget about this. So this is like the tortuosity of that object. And the other thing is you can talk about the connectedness, like the topology, right? So, it's got ends and the branch points. So I can just connect those ends and branch points with something similar to the original one. So I get, from the one object, I can get 3 different objects, right? This describes how convoluted it is. This describes how connected it is. Right? And this thing also has a mass, and it's got a size. They're all the same size. It's got another dimension. So you have 2 dimensions, 3 dimensions, but only 2 of them matter because the density dimension, so the number that decides density is equal to the number of tortuosity times the branching connectivity of it. Right, so those 3 things are connected together by an equation. So you can put together the final object from these 2 objects. So for a polymer chain, this d min, the connectivity dimension is 1. So the connectivity tells you what it is. So 1-dimensional means it's a linear chain. Like for a disk, the minimum dimension would be 1. The short circuit path is a straight line, and it's a 2. Right. And then, so basically that's how.
Is so the DF, the fractal dimension, is that like the complexity of the chain, or like the?
DF just gives you the density. So if you have, if you want to know the density, right, it's going to be the mass by the volume. And the volume is like R cubed, and we said like mass goes with R to the DF, right? R to the DF. So the density is going to be R to the DF minus 3 times some prefactor of pre-density. Right, so DF is just the density. So in other words, it's saying if DF's 2 for a disk, DF's 2 for the squiggly thing, means if I spin this disk around, right, and leave it in a circle, those 2 objects would have the same density. It also says, so basically, say DF is 2, right, and then this thing's rho naught over R. The bigger the object is, the lower the density. So the longer my polymer chain is, it has less and less density because it's not filling space. So the space part gets larger, gets higher than the mass part. Just like if you have a rod, and you spin it around in 3D space and get the density of it, well, a longer rod is going to have a lower density than a shorter rod. And when it finally gets to be just a small object, like the 3D part. So we end up with this equation is going to be R to the DF minus 3 is a power of R to get the density. And the only thing DF gives you is the density. There's no information about what it is. It's just saying the density of the disk and the plate and the spaghetti are the same, but they aren't the same, right? So if you have these other dimensions, like you can say C here is 2 and C here is 1. It's a 1D, it's a linear polymer chain. So C is 1 and the disk is a 2D object. If you take a sheet of paper, C is 2. If you crumple up the paper, C is still 2. That's got to do with what the thing is. It's like a donut and a coffee cup are the same thing. They have the same circular shape, kind of. You squish them right. And then, but the D min, the convolution of it went way up when I crumpled it. So the DF went up when I got like this. So it got a higher density when I went to this because D min went up. But C is still the same. I can still uncrumple it and still have a sheet of paper.
Yeah.
You know, so basically, it's a way to look at things that kind of allows you to say what's different things are. It's like if you have like in proteins, you have like beta sheets or 2D, and then unfolded polymer chain is also 2D if it's a Gaussian chain. But in the one case when it's unfolded, it's a denatured protein, and this is a native state protein. So basically, this is the egg. when it's in the shell, and this is after you whip it up and make a froth with it. Oh, sorry, yeah. So, yeah, so I mean, an example is like if in biomolecules, like you have beta sheets, and then you have, so mostly, we can talk about this tomorrow next time, yeah, but, so let's quit there. We're out of time.